In-class activity 14A, functions with fractional exponents. Think about the amount of food that different animals need to survive. How do you think the amount of food a mouse needs, for example, compares to what an elephant needs? If one animal is twice as big as another, will it need twice as much food? Well, basically, we could say that the larger animal is going to need more food. So I'm just going to print that here. Larger animal will need more food. Objectives for the activity. You will understand that for functions of the form y equals k, a to the x to the a, where a and k are constants, rescaling the independent variable results in a proportional rescaling of the dependent variable. You will be able to evaluate and interpret expressions written with fractional exponents. 2. Kleiber's law describes the relationship between the mass of an organism and the organism's metabolism. For animals, the law states that the metabolic rate is proportional to mass using the following relationship. R equals 70 times m to the 3/4 power. In this equation, m represents the mass of an organism measured in kilograms, and R represents the metabolic rate of the organism measured in food calories or kilocalories per day. The metabolic rate is the rate at which an animal expends energy. Part A. Use the function to complete the following table. The function, I'm just going to highlight it here, just put a box around it, is the R equals 70 times m to the 3/4. So we want to find the metabolic rate. So we're going to take the rate of, it's a dog first. So the metabolic rate, and I'll just put an m sub d for this, and that is going to be 70 times m, which is going to be the mass, 16 to the 3/4 power. Now, if I go over to my calculator, let me clear all this, and we're going to take 70 times 16 raised to the, that doesn't look right. Let's clear that. How about 70 times 16 raised to the 3 divided by 4 power, and we get 560. Let me go back to the paper here, and I'm going to write equals 560 and put 560 in the rate there. Let's do this again. If we do the metabolic rate, this should have been an R here, sorry about that, the rate. So why don't we do this? The rate of the, what's next, the horse. That's going to be 70 times 256, and that's going to be raised again to the 3/4 power. And let's go back to the calculator, and it's going to be 70 times 256 raised to the 3/4 power, and we get 4,480. So 4,480, I'll put that here too. And once more, the rate for the elephant, and that's going to be 70 times 4,096, and that's going to be raised to the 3/4 power. One more time, back to the calculator, and we get 70 again, times, this time we're going to plug in 4096, and this is raised to the 3 divided by 4 power. 35,840. So 35,840. All right. All right, why don't we continue here? I'm going to leave the equation there at the box around it at the top in case we need it, and the chart. So in the part B, it says, how does the mass of the horse compare to the mass of the dog? And also, how do their metabolic rates compare? So the mass of the horse, So let me just do it like this. This is part B. So the mass, I'll use that M there, and the horse, how does that compare to the mass of the dog? Okay, mass of the dog. So we can write this, the mass of the horse, looking at the chart, I'm just looking at that right there, it's 256 kilograms, and then 16 kilograms. Well, if we reduce this fraction, we know that we get 16 squared is 256, so it's 16. And what this means is the mass of the horse is 16 times the mass of the dog. Now, in terms of metabolic rate, so let's do the rate of the horse compared to the rate of the dog. And then now I'm looking at the metabolic rate column here. And we get the rate of the horse we found to be 4,480. 4,480, there we go. And then the dog is 560. Again, we're going to reduce this. And when we do, we get 560 goes into the numerator 8 times. And this tells us the metabolic rate of the horse is 8 times that of the dog. Let's move to part C. How does the mass of the elephant compare to the mass of the dog? And how do their metabolic rates compare? So the mass of the elephants, so we'll do mass, so E for the elephant, and this is going to be compared to the mass of the dog. So the mass of the elephant is 4,096. The mass of the dog is 16. And if we reduce this, we get 256. So we can see the mass of the elephant is 256 times that of the dog. Now, in terms of metabolic rate, the rate of the elephant compared to the rate of the dog, the rate of the elephant, let's see, is 35,840. And the mass, or the rate of the dog is going to be 560. And again, we'll reduce this fraction and we end up with 64. This tells us the metabolic rate of the elephant is 64 times that of the dog. Let's move to part D. And I'm just going to scroll up a little bit here. So part D, if an animal doubles its mass, how do its requirements for food change? We could say if an animal doubles its mass, it would need how much more? Let me see. If an animal doubles its mass, how will its requirements for food change? Well, if an animal doubles its mass, it would need 2 to the 3/4, which is about 1.68 times as much food. Part E, suppose the mass of one animal is K times the mass of another. How do their metabolic rates compare? Write your answer in a complete sentence. Let me just scroll this up here a little bit. There we go. Well, if we want to compare these, why don't we go 70 times, and we'll put one on top like this to the 3/4, and then we'll go 70, and then times m to the 3/4. And when we simplify that, we can get rid of 70s. And for right now, at least, we're left with the km to the 3/4. We have m to the 3/4. And then this can simplify to k to the 3/4, m to the 3/4 over m to the 3/4, which leaves k to the 3/4. And if we write this in a complete sentence, we could say the metabolic rate of the larger animal is k to the 3/4 times the metabolic, there we go, metabolic rate of the smaller animal. Part 3. In preview assignment 14a, you worked with the function h of m equals 241 times m to the negative 0.25 power, where h represents the approximate number of heartbeats per minute and m represents the mass of the animal, measured in kilograms. For small animals, their weight is often measured in grams instead of kilograms. Part A. There are 1,000 grams in a kilogram. Write the function so that it is a function of mass measured in grams. Well, if we do that, and what I'm doing is I'm just starting with this. I'm drawing a little box around it here, and we're going to adjust this. So it's going to be h of m equals 241, and then it's an m over 1,000 to make the adjustment, then negative 0.25 is the power. So for part B, use the function from part A, which we just wrote, to complete the following table. We want to again find let's see, the heartbeats or heartbeats per minute. All right, let's start with the mouse. I'll just work over here. And we're going to have h of, and the input is 18. And then, oops, sorry about that, equals 241. That's 18 over 1,000 raised to the negative 0.25 power. So if we go back to our calculator here, and then we're going to start with 241 times 18 over 1,000. And then we're going to raise this to the negative 0.25 power, hit enter, and we get 657.9. How about 658? So we'll do this, and we'll put 658. And we'll put the answer there. Let's do the same thing. We'll do the hamster next. Let me put it here. And then we have h of, this time it's 60, equals 241 times 60 over 1,000 raised to the negative 0.25 power. Back to the calculator, and why don't we do this? How about we go second entry, and then we'll just make the adjustment here. This needs to be 60, and then we just hit enter, and we get about 248. I'm sorry, 248. 486. I don't know where that came from, but it's 486.9. 486.9. And the rabbit and the cat, their beats per minute are found similarly. And I worked those out ahead of time, so we can just plug those in here. I'll just tell you the numbers. We get 244 for the rabbit and 203 for the cat. Part C, how does the mass of the mouse compare to the mass of the hamster? Maybe we should read that. Part C is, how does the mass of the hamster compare to the mouse? We've always been putting the larger one first. So if we look at the mass of the hamster, so the mass of the hamster to the mass of the mouse, we're going to get 60 grams over 18 grams. And if we reduce that, 60 over 18 simplifies to 10/3. It's a 3 there. So that tells us that the mass of the hamster is 10/3 that of the mouse. In terms of heart rate, so if we heart rate of the hamster, heart rate of the mouse, so then we're looking at beats per minute, and we're going to put the 486.9 beats per minute over the 658. And when we divide that, 46.9 over 658 is about 0.74. Part D, how does the mass of the cat compare to the mass of the hamster? How do their heart rates compare? So I'm going to scroll this up. I'll stop right there. So for part D, how does the mass of the cat, so the mass of the cat compared to the mass of the hamster. So the mass of the cat is 2,000 over the mass of the hamster, which is 60. Reducing this, we get 100 over 3. So the mass of the cat is 100/3 times that of the hamster. And in terms of heart rate, the heart rate of the cat compared to the heart rate of the hamster. Again, we're looking at the beats per minute here. The heart rate of the cat is 203. Heart rate of the hamster, 486.9. And we get just about 0.42, 0.42. Part D, well, the second part D, so we're at that part D. If an animal is double the mass of another animal, what is the effect on its heart rate? Okay, so what we could do to start answering the second part D would be to work with the heartbeats per minute equation or function. So we could write 241, and we need one mass to be twice that of the other. So I'm just going to write 2m over 1,000, and this is to the -1/4 power. And then again, I'm going to write 241 for the denominator. Now this time the mass is half that of the other one. So that, and then -1/4. Now if we get rid of the 241s and just start simplifying this, we have 2m over 1,000, -1/4. And then we have m over 1,000 to the -1/4. And let's get rid of the negative exponent. So why don't I move the denominator to the numerator, and that's still 1/4 there. Now it's going to be 1/4. And then 2m, this goes down to the denominator. Exponent is positive. And then if we start simplifying this, let me just come down here and work. What do we have? M times 1,000, 2m times 1,000, and this is all to the 1/4. Thousands go, the m's go. I'm left with 1/2 to the 1/4, and there's different ways we could write this. We could even write this as 2 to the -1/4 power, and that's approximately 0.84. Okay, let's scroll up here to part E, and it says, suppose the mass of one animal is k times the mass of another animal. How do their heart rates compare? Express your solution in radical form. Okay, so we're going to do the same kind of thing again, making a ratio with this function, and then we're going to put one of these, let's see, m over 1,000, and this is to the -1/4. And then we'll do 241, and there's no k in this one. We'll leave that out. We're comparing these, and then -1/4. Now, start simplifying this. We can do the same kind of thing. We are back to the numerator. We get k to the -1/4 power, and then we have the fraction m over 1,000, -1/4. And then m over 1,000, -1/4. And these cancel, we can see that, and we're left with k to the -1/4 power, that's a negative sign, and we want to express our answer in a radical form. So we have 1 over the 4th root of k. Part 4, the relationship between the volume of a sphere and its radius can be expressed as v is equal to 4/3 pi r cubed, where r is the radius of the sphere and v its volume. If we solve the equation for r, we see that the relationship can be expressed as, I'm just going to copy this down here, r is equal to 3v over 4 pi, and this is to the 1/3 power. Determine the radius in centimeters for a sphere with a volume 137.258. So what we have to do is we have to take this equation, 3 times volume is 137.258 over 4 pi, and raise that to the 1/3 power. So one more time, we're going to go back to our calculator. Let's clear this and start anew. And what do we have? We have a fraction, so we're going to take 3 times 137.258. And then the denominator is 4 times pi. And we're going to raise all of this to the 1/3 power. So 1 divided by 3, and about 3.2. We'll say 3.2. So back here, 0.2. And that is the end of this lesson. Thank you.